Okay, so I'm here substituting for Graham today because he's traveling. And yeah, we can just get right into it. So as everyone here knows, NLP models now are like really deployed at a large scale. And we all know that training big models is expensive. I'm sure that you've experienced that in homework one and in anytime you train a network, a deep network, you need GPU resources, and this is something that we all understand. But something that I think is overlooked is that inference. So once you have a trained model, now deploying it and making predictions for users is arguably even more expensive. Like if you look at the lifetime of a model, it probably exceeds the training costs according to this analysis within just 1 week of use. And so if your model is being used for months or years by many people, the cost will like greatly eclipse the training costs, which is more of a one-time cost. And this is a problem because if we want to make AI systems able to help lots of different people in different places, people without as much resources or access to power, we want to be able to reduce the cost of serving AI systems to the public. And this is also getting harder because models are getting bigger. There's been like maybe a slight shift towards reducing model size a little bit in the last maybe 2 years, but these models are still like billions of parameters in size, and that is expensive to serve. So the main question of this that we'll be talking about in today's lecture is how can we cheaply, efficiently, and equitably deploy NLP systems without sacrificing performance? And there's like a clear answer here that I'm kind of leading towards, which is model compression. And model compression here basically means taking a trained model and then reducing the size of that model before deploying it. And there's three high-level ways that we'll talk about in today's lecture for how we can compress models. The first is quantization, which is you basically don't really change the architecture or parameters of the model up to a certain amount of precision, and then you throw away the remainder of the precision. The second is pruning, so throwing out entire components or parameters of a model. And the third is distillation, where you might change all of the parameters, but you're basically condensing the knowledge of a big model into a smaller model that is retrained often from scratch to replicate the behavior of the big model. And don't worry, I'll go into much more detail with all these things. I think the mic stopped working, so I'm going to speak up. If anyone's having trouble hearing me, just please raise your hand. And yeah. Okay, so I've motivated this idea of model compression, which is very tempting, right? Just take a model, make it smaller, get the same performance, and it's just cheaper to serve, right? Nothing about that seems bad. So I think there's a natural question of why is this even possible? And specifically, I think a natural question is instead of taking a big model and making it smaller, why not just start with a small model and train it as such? Like that seems a little more intuitive. So that's the first question is why not just start with a small model that we train? And then the second question would be, why is it possible to take a big model and throw pieces of it away without sacrificing accuracy? That does not seem like a given that should be even possible. And I'll just give you a little intuition for why this is possible. So this term overparameterized means how many people are familiar with this term? You can raise your hand. The basic the meaning of this term is that you have a model that has usually more parameters than you have training data. or in more casual terms, you just have a lot of parameters, like way more than statistical machine learning would say you need. So for example, like GPT-3, the original GPT-3 model had 170 billion parameters, which is like definitely overparameterized. And so there's been a lot of work in the theory community of ML that shows that overparameterized models that have a huge number of parameters, are actually much easier to train, especially for very complicated tasks. And the basic idea is that training deep neural networks for most tasks requires optimizing a non-convex objective, which is not guaranteed to, you're not guaranteed to find the global optimum of a non-convex objective. But when you have a bunch of parameters and you're trying to basically tune the parameters to find the best value of your objective, having a lot of parameters sort of lets you sidestep around saddle points or local optima that are not global optima. You can basically like take sort of shortcuts around barriers in the optimization space. This is sort of the intuition, and the CMU's convex optimization class goes into a lot more detail for this kind of thing. Anyways, I think the intuition here is that models with a lot of parameters are easier to train and they lead to better models. But you probably don't need all those parameters for inference. They're more of a training time trick. Okay, so now before I move on, any questions about the motivation here? Okay, so we'll start with quantization. And the most obvious way to do this is post-training quantization. So you train a model as big as you want, and then you just reduce the precision of, say, all of the weights in that model. So for example, where we can revisit this slide that Graham had shown two lectures ago on, if you have a 65 billion parameter model like Llama 2, and you have, say, 4-bit precision, so 4 bytes of precision, so like 32-bit floats. Just loading that model into memory would take 260 gigabytes of GPU memory, which is more than most single GPUs that you could buy have. But if you instead reduce the precision of the parameters of the weights in that model, you see like a pretty massive decrease, which is linear to the reduction in precision. At the most extreme case, if you replaced each float 32 with a single bit, so 0 or 1, then you would only have like an 8 gigabyte model, which you could probably load into most GPUs. And so I think there's clearly an attractive proposition here in terms of the cost. But before we go into some of the nitty-gritty here, just a refresher from computer systems. So neural nets typically represent weights as floating point numbers in order to express, to have a broader range of values in the model. And so floating points, in at least in like the IEEE standard, which is the most common, you have 3 pieces. You have like a sign bit, which says is it positive or negative, a fractional bit, a fractional piece, which specifies sort of the, it specifies the range of the values, and then the exponent, which scales how big or small the float is. So we can give an example here. So here we can do float 16, where we have like 10 bits of fraction. So this gives a lot more range of what the number could be. Then the exponent bit is 5, so you have up to like 2 to the power of 5 or 2 to the power of -5 as like the scaling factor here. And then the sign, which is +1 or -1. And so float 16 is pretty common, but for machine learning, it's often not enough, because especially when you're trying to train a neural net, you often have very small or very big values like underflow or overflow. And therefore, a really popular data type that was designed just for machine learning is called bfloat16, which just like moves. The idea is you're just moving some of the bits from the fractional part to the exponential part, so you can have a larger range, but within that range, you may have a fewer choice of values to choose from. But it just works. It supports like some of the problems that we face in machine learning. Anyway, so this is floating point types, but as you can probably imagine, once you get below 16, you're really impacting the amount of things you can represent in a float, given that you need like one thing for the sign. And then if your range of the exponent is small, then you don't have that much of a range of values you can represent at all. So a really popular way to like get really small amounts of footprint in models is by quantizing to integers. And this is not that obvious because you're taking a float and turning it into an int. And so one way this is done is called ABS-max, or absolute maximum quantization, where you basically map each number in a list of floats to a range of integers. So for int 8, the range would be like -127 to 127, because that's 255 total values, and 2 to the power 8 is 256. And here you basically find the absolute value that is largest in the whole array, and then that becomes 127, or whatever the largest value in your integer range is. And then everything else becomes assigned to the closest integer that's like scaled by that value. So here, for example, in this example, we have 20 is the largest value, and so 20 would become assigned as 127, and then everything else would be assigned proportional to that. So like 0.5 is 1/40th of 20, and 1/40th of 127 is rounds to the nearest number of 3. And so this is kind of how you can go beyond floats and actually represent parameters with ints. The most extreme example, which should also now highlight some of the issues with this idea of post-training quantization, is what if we just had a binary value for every parameter, 0 or 1? And so instead of so we might train a model using floats, and we get these parameters. So we have the purple here is like the hidden states, and then the red would be the activations. And these are all between 0 and 1, right? But if we now round them to the nearest value, 0 or 1, we get on the top there a list of binary values. And this seems like really attractive, right? Because you only need 1 bit per vector. It's like really small. But now let's consider like a real example here where we are trying to do translation, and then we are producing these float valued hidden states and activations. In this example, if I just rounded up or down each of the values, the output vectors the embedding vectors that we would then decode to outputs, even though they're very different in the original float space, they actually become all the same thing here, which is definitely not what you want. So basically, by reducing the precision, you might be like significantly impacting the range of things you can express. And this basically does not work. Like turning a complex set of floats, of high precision floats, to binary numbers does not work. And later I'll show that there are ways to make this work that are a little more complicated. They just require more processing after the initial training of your model. Okay, so now that I've motivated this problem, we can talk about a few like methods that actually work for post-training quantization. The first one belongs to a class of methods called model-aware quantization. And the idea here is that if you can study the statistics of your model, you can sort of learn ways to represent values in a way that is matching the actual learning, the actual distribution of weights in that model. So for example, with BERT, most of the weights in each layer are are concentrated around like the mean value there, and you have a few weights that are very far from that mean value. So you can sort of fit a Gaussian distribution, normal distribution to the distribution of weights. And then only a few weights in each layer will be at the tails of this distribution. So the idea here is that therefore, and for just to motivate this a little more, if you have values at the tails of the distribution, they pose issues for quantization, because like if you're using the abs-max quantization I mentioned before, you're now defining your range according to the minimum and maximum values. And then everything in between, which might be close together, will now be grouped into the same bucket. And that throws away a lot of the ability to distinguish between weights in your network. So the idea here is that you basically store the outliers separately, and you actually store them in full precision. So you're like paying the full storage cost for a few parameters. And then everything else that's like sort of concentrated together gets quantized into a much lower precision space. And I think that this is, at least in theory, very effective, and they have strong results here. And however, a problem with that approach is that you're defining like the outliers and the minimum and maximum for each layer uniformly. So instead, this LLM.int8, which is actually very popular in NLP, you might have heard of it if you have been building NLP systems. They go a step further, and they, instead of quantizing each layer uniformly, they quantize each row or column of a vector in matrix multiplication separately, with the motivation that most of the parameters in transformers are for matrix multiplication. And so by doing this, they're able to actually get a better quantization, because you're able to like have a more precise space range of the values for each row or column of a matrix. Yeah.
Just curious, in the previous slide, why exactly is the frequency range changing based on the layers?
Based on the layers. Different layers might have more concentration of weights to a single value, or like the values of weights in that layer might be concentrated or might be more broad. I think that's how to think of it.
Is that inversely proportional to the layers in the front? Like, because the layer 5 has a very high frequency compared to layer 10.
Mm-hmm. Yeah, I think that's right. I think that the this paper also discusses that problem, that as you get later into the layers of a network, you see a lot more of these outliers, these large magnitude values. Okay, so moving on here, the last thing I'll say is that there is like an overhead you're paying when you're doing this kind of quantization, where you have to, for each vector, you are now mapping it to a list of numbers, and you need to then decode those numbers back into floats, like decode your ints back into floats. So there's an overhead that costs time when you're doing inference. So if you have like a small model, this is not going to help you go faster, most likely. But if you have like a really big model, it can actually like double your inference speed at least. And it also lets you load models into memory that you otherwise would not be able to. So there's like definitely a trade-off in when or this is really desirable. Any questions here before I move on to some more high-level stuff on quantization? So in terms of hardware concerns, I think one of the challenges, like if you're somebody who's interested in algorithms, you might have very creative ideas for how you might do quantization. But the problem is that the ability for quantization to actually be effective or make things faster is largely limited by both hardware and also like low-level systems, like the framework, like PyTorch that you're running your models on. So at a hardware level, some data types are like basically just not supported by hardware. Like int3, like a 3-bit int, is not something that processors generally support. So if your quantization method uses int3, it's effectively just using int4, and then you're not getting a speed up there. And then PyTorch has its own requirements. Like PyTorch doesn't have int4. A lot of modules don't support quantization at all in PyTorch, like something like an RNN, which is now like becoming popular again. It's not really supporting quantization right now. So you definitely, if you're trying to go this route for a practical application, you'll want to know what your hardware is, what your framework is, and what you can actually support with the ways you want to compress your models. And one last thing I'll say is that both of the methods I showed so far, they both have to they have their own customized hardware accelerators that they wrote to make those things work. And this is like a lot of work, and most people probably don't have the time to do this. So there are methods that I haven't shown here that do quantization in a way that is effective without having to rewrite your framework or your hardware accelerator. But this is definitely something to consider with quantization. Okay, so now I think I've motivated why post-training quantization is hard, because you're throwing away precision, which can make it hard to get the most out of the network that you have trained. So a tempting idea here is, now we know that, let's say we know we're going to quantize our model. Let's train the model with quantization in mind. And now we can revisit the example I showed before of binarized neural networks, which didn't work. But it actually can work if you train with the binarization in mind. So a paper in 2016, they considered a case where all of your weights were -1 or 1. Activations were also -1 or 1. And they do some clever statistics to make that work. And then the gradients that you backpropagate through the model are also negative, they're also discrete. And so it's probably kind of surprising that this works, but they basically are using the core mechanisms that we use to train neural networks and using fancy statistics to make this work for binary values. And by doing this, they get kind of shockingly good results. Like on CFAR10, which was a very popular image classification data set for a while, they get a 10% test set error. And at the time, a state-of-the-art method was at a little under 12%. So they're basically matching or beating some of these extremely strong models at that time. And they used effectively the same architecture from some of these models, but just binarized. So this was sort of a proof of concept that if you quantize during training, you can match performance and get a much smaller model, which I think was a really surprising finding. And then a more recent work that I think is really cool is that for doing quantization, another thing you can do is you can start with your model that is full precision, not quantized. And then you can basically train each layer, one layer at a time, to replicate its counterpart in the full precision space. So you can run inputs through the full precision model. You get the output, the probabilities of each word, for example. And then you replicate your quantized model to reproduce, to get very close to those same weights. And then you do this at the second layer. So now you have the logits from the hidden states from the second to last layer, and then you train your quantized layer to match those hidden states, and you keep doing that all the way down. And I think the intuition here is that by doing layer by layer distillation, you're sort of replicating not just the output, which is kind of sparse and hard to replicate, but even the the flow of data throughout the whole model step by step. And you can replicate that into the quantized model, which may run into issues when training just end to end. And then the last work here, which Graham already talked about 2 lectures ago, what is QLoRa. So here They use parameter efficient fine tuning to train a highly quantized like 4-bit model, and they do a bunch of other fancy tricks. And QLoRa is like super popular right now, so this is probably the, if you're going to use a quantization method today, this probably would be it. Okay, I think I'm going to move on to pruning now. So any questions here? Okay, so pruning is pretty different than quantization. In quantization, you are sort of like chipping away at every parameter in your model. Instead, in pruning, you're like completely eliminating some parameters and completely not changing everything else. So a number of parameters set to 0 and the rest are completely unchanged. And the most intuitive way to do this is this idea that if you have a bunch of parameters, some of them are probably close to 0, in which case they're not doing anything anyways. So just make them completely set to 0. That way you can ignore those parameters effectively. They effectively are not doing anything, and it's as if they don't exist. So in magnitude pruning, you set to 0 some percentage of parameters that have the least magnitude. And in like machine translation, people have seen that you can remove almost half the parameters in a model and get almost 0 change in your downstream performance, which I think goes back to the earlier point about overparameterization. Like you need a lot of these parameters for training the model, but in practice, they're not really doing too much. And so you can just get rid of them. And so this is a type of unstructured pruning where you're just you're removing parameters throughout the model anywhere you see fit. There's no structure to how you're doing the pruning. And this is related to the lottery ticket hypothesis, which was this idea that when you train a full model, there are like randomly initial, there are subnetworks of that model that the idea is that when you're training a big model, there are subnetworks that are actually a better initialization than the initial model. So it doesn't, it's a little bit unintuitive that if you have, let's say, a model with 100 billion parameters, there's subnetworks of this model with, even if you randomly initialize them, that might say have 1 billion parameters, like 1% of the size, that are actually better than the full model. And so this is related to pruning, but here they prune the model, then they retrain it, and they find that surprisingly, like here, a model that is 20% the size, so it's pruned to 20% of the original model's parameters, and then retrained, is actually like more effective and generalizes better than your original model. So the idea here is basically finding like really good initializations of these subnetworks can be better than like the most intuitive random initialization of a big model. And so this is sort of a step beyond pruning where you're pruning a model, then training on top of that, and that can improve performance. But generally, pruning, I think, is not a method to improve performance. It's a method to maintain performance while improving the efficiency and the size of your model. And so there's been like a lot of cool work in pruning coming out of CMU recently. This paper called Wanda, which came from folks in MLD. The idea here is that magnitude pruning presumes that you can just decide which parameters you want to throw away based on how big they are, but it doesn't consider the fact that there are systematic differences in the size of inputs that come in. So in the paper, they gave a nice example, which maybe I'll write on the whiteboard here, which is that if let's say your model was just this basic 2-parameter model, X and Y, and you had weights A and B. And let's say we know that the magnitude of A is like a lot bigger than the magnitude of B. Then in magnitude pruning, we would just set B to 0. And then the model would just become A times X, because the idea is that this parameter has a lot more effect on the output, and therefore we don't need to consider the other one. But what if I told you now that the range of X, like the average value of X, was 1,000? The average value of X was 1, and the average value of Y was 1,000. Now, in practice, even though B is smaller, it's processing much larger inputs, and therefore it's going to have an outsized impact on the output of the model. So that's the motivation of Wanda, which is here they decide which parameters to prune based on a combination of the magnitude of that parameter, as well as the magnitude of the actual inputs that come into that layer of the model. So they take like data, calibration data, and then they kind of say learn what the average magnitude of the inputs are, and they use this to decide what parameters to prune. Okay, so so far I've been talking about unstructured pruning, and I think there's a pretty clear problem with this that makes this really not that effective in practice. And the problem is that you can make a model sparse. You can take the vectors and make them sparse. But if your hardware does not take advantage of that sparsity, then you're not getting any gains in performance. So for example, here we like turned off half the parameters. But if we're still multiplying zeros with other zeros in like a dense operation, we're doing exactly the same amount of work. We're getting no benefits here. And the reality is that right now, hardware for machine learning does not support sparse data structures or computation that well. Like matrix multiplications do some kinds of complicated things under the hood. And therefore, they don't really work that well for sparse data structures. And so basically, right now, this is not very effective in the current hardware, although I hope this will change in the future. So therefore, like a more immediately useful idea is called structured pruning. And the idea here is that instead of just picking parameters across, like willy-nilly across the whole model, you remove entire components or entire layers. And therefore, you're pruning the model in a way that is structured and really going to make a difference on your overall runtime. So Graham and one of his PhD students a few years ago did some really cool work on this, where they showed that if you're training a transformer model like BERT, you usually have many heads of attention. Like you guys also experienced this for the llama homework, where you had, I think it was 8 heads of attention there. But in practice, most of these heads of attention can be removed without really any negative impact on the performance of your model. And so here they show that for an MT model, you can remove half of the attention heads entirely and get a negligible impact on your performance. This is different than what we showed here, where we were removing parameters from anywhere in the model we saw fit. Here, we're removing entire heads of attention. Even some of those heads might have large magnitude weights, some of them might have small magnitude weights, but we can just remove the entire attention head, and this has an immediate impact on the performance of your model. And generalizing this, recent work has proposed controlling even other kinds of components of your model. So in this paper from 2 years ago, they propose masking, having 2 levels of masks on your model. The first is like what they call a coarse mask, which is turning off large components like full attention heads or full feed-forward layers, where you replace them with the identity matrix. And these are like really big things to turn off. And then you could also have fine masks, like sorry, I meant entire self-attention layers, not attention heads. And then the fine masks would control like individual heads or removing individual dimensions. So changing your hidden state to be from like 512 dimensions to 200 dimensions. And so the idea here is they give two different levels of granularity at which you can turn off different components. And then these masks then learn using some kind of held out validation data to learn what can we turn off without like totally destroying the performance of this model. And in this paper, they showed that you can really get pretty far with this idea. And the last thing I'll say about pruning here is that methods like this, you're actually learning a kind of control over your model. So you're learning this set of masks, and that's pretty expensive in terms of training budget. It requires a lot of GPU memory. And so if you want to prune, let's say a Llama 70 billion model, you'll need basically as much compute as it took to train that model to begin with. So this is a recent paper from Graham and one of his PhD students, where they instead ask, can we do pruning without having to like compute gradients at all? So basically, if we just have enough memory to run the model on our computer, can we then use that same computer to prune the model without having to use Atom or to compute gradients? And so I think the idea here is really clever. They basically randomly mask out all the different modules in the network. So they like create like 100 or 1,000 variants of this model with different masks turned off. Then they measure the performance of those like perturbed models. And then they learn a regression of like how much does each module affect the performance of the full system. And then you can then use these regression weights of this learned regressor to figure out which modules you can actually turn off without impacting the performance too much. Okay. Any questions here?
Just doing like a validation forward loop on these prune models?
Yeah. Like randomly prune models.
So remove our model. What happens to the matrix multiplication part? Do you just multiply with identity instead? What is it?
Yeah, that's right. Like it depends on I think like for self-attention heads or for feed forward layers, you could think of it as just multiplying by the identity. And next I'm going to move on to distillation. If there's any questions about anything I've covered in pruning, you can ask now. And I know I was moving pretty fast, so I'm happy to talk.
What's the point of learning or regression? Like, does it generalize to other models at all, or what's the purpose of it?
Yeah, the idea is that, so the best way to do this would be to consider all possible choices of masks, like turn off every combination of modules and then measure the performance. Then you know exactly which combination is the best. But if you have tens of layers and tens of components in each layer, you'll have like millions of different submodules you want to try out. So this lets you just sample from that space, combinatorial space, and then predict the interaction between what you have seen, between the modules based on what you have seen.
So like slightly more optimized than some kind of random search.
Yeah, I think that's right. Yeah. I think you can make an analogy for this to like parameter selection, where you can do random search, but now people do much like fancier things like Bayesian optimization, which are trying to explore the space in a more structured way. And so I think that this is similar in spirit.
Do you know the plot trees like the, so are you like randomly just choosing like for example the green one does better it seems, so is it just like you're retaining 80% of the parameters randomly, or?
You're retaining 20% in the green line, so you're throwing away 80%. So in the like what this green line exactly means, and I did not go into detail here, is that you first train a full model with all of its parameters, and then you apply pruning methods, kind of like magnitude pruning I showed before, to find like a good subnetwork that is still pretty effective after training. But then they do something weird, which is then they then restore that subnetwork to its initial random initialization. So in the beginning, you had so you train this model and you initially initialize it randomly. So you might have just random values at each parameter. You then train the model as it is. So these parameters are all changed and they serve the task. Then they identify a good subnetwork here. So you might throw away this node, you might throw away this node, maybe this node. And then you say, okay, what was the initial initialization at these exact parameters, which I've since learned better parameters, but what was the initial value here at the start of the optimization process? They then go back to those initial values, retrain the model on this task, and it becomes even better. Which I think it's there's been a lot of like theory about this since this paper came out. It was kind of like a very influential paper. I think to me, this shows at the very least the importance of initialization and how much like randomness there is in neural network training and how you can kind of take advantage of that.
Yeah, how is that related to dropout?
So I think you can see dropout as a version of pruning where at each step of optimization, you perform a random pruning. You like randomly prune your network for each update, and then you then you update the parameters that have not been dropped out. But then in the next step, you have a totally different prune network. So here you're doing pruning once, and then you're training this fixed prune network for all of the iterations. Whereas in dropout, you're doing like a random pruning each time. And they serve different purposes is the main difference, where pruning is primarily for reducing the size of your model, whereas dropout is primarily for regularizing your model to avoid overfitting certain to individual weights. Like to avoid individual weights having too much correlation with the label. Okay, so I'll move on now to the final piece here, which is yeah, so the last slide I forgot to show here is that, which I think is a kind of a summarization of everything I've taught so far about pruning, is that Wanda, which is this unstructured pruning way that I showed earlier, even though it achieves the same number of parameters as like a structured pruning method, which is Bonsai, the one from Graham, it actually achieves much less of a speed up, potentially like a negative speed up. Whereas a structured pruning method with the same amount of parameters can be like a lot faster. Like 50% speed up is huge. So I think that this shows that like unstructured pruning can be pretty ineffective if it's done naively. Okay, so now I'll move on to the final piece here, which is distillation. So in distillation, the core idea here is that you're training one model to replicate the behavior of another model. And this is pretty fundamentally different than the other two methods we talked about so far. In distillation, you're probably changing every parameter in your model. You might even be having a totally different architecture. In the other two methods, in quantization, you're like kind of not changing any of your parameters up to a certain amount of precision. And in pruning, you are keeping a set of your parameters completely fixed. Whereas in distillation, you're like changing everything, but hopefully doing it in a way that requires many fewer parameters. And distillation is related to a really cool idea that is more classic machine learning called weak supervision, which is the idea that if you have unlabeled text, or it could be images or whatever data you want to process, you can produce like things that are like labels that you could use like labels, but maybe are not actually written by humans. And then you can train on these as if they were labels and actually get pretty good performance. A few like really famous examples of this is one is self-training, where you initialize like a model, maybe with a handful of points, like 3 or 5 examples. You train a classifier on that very small number of points, which is going to be really bad because it's not enough data to learn. Then you have that model make its own predictions, which are probably pretty bad on a bunch of unlabeled text. You use those pseudo labels to update the model again, and you can do this iteratively. So you're like basically using a model to produce its own training data to train itself, and you do this over and over. And this is like a pretty classic method at this point. It's like 30 years old, and that's self-training. And then there's a few others that I won't go into, just not to be too dense, but that are related to this. And this is all pseudo labels are also used when you, let's say you don't have the ability to annotate thousands of examples, but you can write like a basic rule. So you might say, if you see a movie review that says awesome, it's positive. And if it says I hated it, it's negative. This is probably not a good rule to apply for your actual classifier, because as Graham had showed earlier, this is like really brittle. It requires a lot of work. But you can use these rules to construct pseudo labels that you then train like an actual full vocabulary model on. And if you have enough of these pseudo labels with enough of these rules, you can actually get pretty far. And so that idea I just described is like there's a startup called Snorkel that does that. And they have a bunch of papers about this idea as well. So so I'm mentioning weak supervision because this, to me, forms the basis of knowledge distillation. In knowledge distillation, you train a small model to just replicate the predictions of a big model. So the big model is producing pseudo labels on unlabeled text, and then that becomes the target for your small model to match. The one requirement here that I think is really important to note is that you do need unlabeled text that matches what you expect as input. So let's say you're doing a movie review classification. You definitely would need to somehow find thousands of movie reviews that look like the kinds that your model is going to expect. And most of these methods require that to work. Okay, so there's broadly like 2 kinds of ways you can train knowledge distillation. The first is like the most obvious, which is called hard targets, where you take your unlabeled text, you produce a label from your teacher model, and then you now use that the teacher's prediction as the target for your model. So you might say, llama 70 billion predicted positive for this review, therefore I'm going to say the label here is positive. This is like really easy, it's convenient, it's very intuitive. But another type of distillation that's even more effective pretty consistently is called soft target distillation, which is that instead of trying to do a supervised learning objective where you're just trying to match the label predicted by your teacher, you instead want your student model to produce probabilities over the full distribution of labels that matches the teacher's distribution over labels. So like here, the llama 70 billion, our teacher, has predicted like probabilities over 3 different labels. And then we want the student model to match those probabilities. I think a cool thing here is that this is usually not possible with supervised learning. When you have the annotator, they usually just give you one answer. They don't tell you how likely it is that they were wrong about that answer. Like they don't tell you what the next best answer was. But with a neural network that's teaching you, you can ask that. You have a lot more flexibility. And then this also changes how it's optimized. So instead of optimizing for like the probability of the correct answer, you can basically optimize for the difference in the distributions over the answers. And as we can see here, in this paper by Jeff Hinton and some others, they use this method for speech. I think it was speech recognition. And they showed that this baseline here is they took a training set and then threw away the labels and pseudo labeled the inputs of the input speech with another model. And then they showed that if you're using hard targets and you use like the full training set's inputs, you can get pretty far. But if you instead don't have that much unlabeled speech and you use like a small amount of speech, using soft targets is like way, way more effective. Okay, I'll just jump ahead to I think a result that is like pretty shocking that it works. So this came from Zach Lipton and some other people a few years ago. And the idea here is that you can take a model that is trained with supervised learning, and here they trained it on like a image classification task. Then you can repeatedly distill it to itself using soft targets. So you take a bunch of images and then predict the distribution over the labels of those images, and then train the model to basically match its own you train the model on a soft target distillation objective using itself as a teacher. And it's still kind of bizarre to me that this works, but they show that this pretty consistently improves performance of a model. So I think that to me, the intuition here is that this soft target objective, which is different than what you were trained on in what you would train using supervised learning, it's like a different objective that is somehow conveying more information to your model. It's conveying like uncertainties about the labels, and it's like a richer knowledge interface between the teacher and the student than just giving a single answer. And that this like rich interface of knowledge can be really effective. To me, that's like the takeaway from this result. But yeah, check out this paper if you think this is cool. Okay, so any questions on what I've talked about so far in distillation here?
The example part is really similar to dropout. The example part, the last part. Yeah, it's really similar to dropout. I think that of the dropout actually the example, but
It's the example.
example. I think it's really similar.
Oh, the onsite. Yeah. Yeah, I think that's right. Yeah. Yeah, if you think of dropout as a way to perturb the model, you have different perturbed versions of a model. Here, they instead produce these perturbed versions of the model by distilling the previous version to itself. And then under that view, it's like they're both just ensembles of random perturbations of the same model. Yeah, I think that's exactly right.
I also have a question about this slide. So you see, if the accuracy of the model is not high initially, then the soft label produced also has a low quality. How can you train the model subsequently using a low quality soft label and get a better result?
Yeah, I think that this method would require like pretty strong initial model to make this work. And then given like a decent enough initial model, it can make it better. That's like my intuition on that. At the most extreme case, if you start off with a random model that produces random outputs, you'll probably never improve performance.
So how accurate should the initial model be? Do you have any information on it?
So I don't have a clear answer, but I think that I would say it probably just has to be a little better than random chance, which is probably a surprising answer. There's a previous work. Let me see if I can find it. Yeah, so this paper I recently read, and it was pretty shocking to me. They take models. Sorry, they focus on, I think, image classification here, and they take an initial data set and they randomly flip the label for like a certain percentage of examples. So like they provide the wrong label in train data for some percentage of examples. And they find like that you can replace 99% of labels with the wrong label and still learn something useful. Which I think is really weird and doesn't make sense. And they kind of show that I think the idea is that this only works for really deep networks. And by the way, these models I believe were not pre-trained, so they were only learned on this terrible data. So I think that so therefore, like if I'm generalizing that finding here, I think that because this suggests that neural nets are very robust to label noise. And if you think of this kind of method as you're using a noisy label from a teacher, you can probably get pretty far with data that is mostly noise, but still better. It's like not pure noise.
Well, more of a comment rather than so for the similarity between this and the dropout, I think like around 2016, 17, Gary Gall and like his friends published a lot on this area. Actually, before this paper, so like if anyone is interested in this area, like the keyword would be like aleatoric uncertainty, epistemic uncertainty, or like model uncertainty. And like major papers would be like MC dropout or like dropout as a Bayesian approximation. So there's that. And also on the label noise side, I think the important premise on the previous paper that you mentioned was giving uniform noise to samples. Like if we start giving some like specific like biased noises, like the neural network tends to be like somewhat like very biased towards that specific noise. But existing computer vision label noise literatures often goes up to like label noise of 90% of something, like already as a benchmark. So even though those cases are somewhat like synthetic, I think it's pretty interesting to see those cases. But still, like they are only injecting like uniform distribution for the label node, so that like theoretically speaking, the model will like with like enough number of iterations, the model will be biased towards the two labels. So
Yeah, that's thanks for the clarification. So yeah, for the recording, the student pointed out that in the previous paper, an important detail is that the noise in the labels was uniformly sampled, and that if you instead use non-uniform random noise, it can actually have a major impact on the ability of a deep network to learn the input label mapping. Yeah, I think that's a really good point. Thanks. Okay, so distillation was originally designed here for like when you had a single label per input. But in text, we often have sequences. Maybe we want to generate a sentence. And so how do we extend distillation to this sequence labeling setting? And so there's like kind of two obvious ways, really. The first is that you want to predict, you want to match the distribution of words that the teacher suggested at each point in your generation process. Given a prefix like this movie is blank, you then see the teacher's distribution over the words and you try to replicate that in your student model. And then the second idea is that you might now have, but the problem I think here is that as you keep generating the text, I think this is related to an idea called exposure bias, which is that as you generate text, the teacher and the student might diverge dramatically. Like the teacher might be generating consistent text and it starts to look very different than what the student could have possibly generated. So the second idea here is sequence level distillation, where you instead just generate a hard target from the teacher. So instead of using like so you use soft targets at the word level, and then at the teacher at the sequence level, you generate a full sentence from the teacher, and you just want to maximize the probability of that pseudo labeled gold sentence. And they show that if you combine these two objectives together, it's really effective. So I think that this seems like the right way to do distillation for like generating sequences of text. And one really popular distilled model in NLP that I use all the time is called DistilBERT. It basically is just BERT, which at the time BERT came out, it was considered to be really big, which is kind of like comedic now. But the idea here was like, can we reduce the size of BERT in half and get the same performance? So they do this. They use a couple of tricks to do this. First, they just like took every other layer of BERT. So if you had a 12-layer BERT model, they took 6 layers, and they initialized each layer from one of the layers of the initial BERT model. So it's not like a random initialization. Then they did effectively soft target distillation, which was effective. They also tried in their paper, and they used they combined soft target distillation with like real supervised objective from language modeling. It's like they masked tokens of text, and they tried to train on both like what was actually behind the mask, but also what the teacher would have predicted for that mask. And they kind of found surprisingly, I think, that the supervised objective doesn't really help much at all. So if you have like a good teacher, that's probably enough for distillation. And then they did something else to make sure that the embedding space like had a similar geometry in the small model and the big model. And the main finding here is that you can do this and get a model that is pretty much just as good or very close to it in most tasks as the big BERT model. And DistilBERT is like super popular. People use it all the time. Okay. So now I'm going to go a little bit off of this initial motivation of efficiency and talk about how distillation can be used to like actually do things that you cannot do otherwise, like unlocking capabilities and performance that are pretty much impossible using traditional learning. Before I do that, any questions about distillation before I move on?
Try to define the architecture of the distill model. If you want to distill some given model, what would your first experience?
I think you have a lot of flexibility in distillation, unlike something like pruning. I think I've seen work that suggests that distillation is most effective when your student and teacher have like similar architectures. Like for example, if your teacher is an autoregressive model, you might like a GPT-2 or 3, you might want your student to be autoregressive. But my intuition is that there's a lot of flexibility here. And especially if you're doing hard target distillation where you're generating sequences, you could just treat this as labels, and then you could train any student model. So I don't think it's that constrained. Okay, so I think the first thing I'll talk about here in this sort of new age distillation world is self-instruct, which Graham already talked about 2 weeks ago. So I'll just touch on this. The idea here is that they are doing like self-distillation, sort of like this paper, where they're taking a model, making it generate data, and then training that same model on that data. That's the basic idea. But here they're doing something very specific where they take a vanilla language model that's just trained to like generate text, and they're trying to teach it to follow instructions using instruction fine-tuning. And the way they accomplish this is by having this vanilla language model first like generate instructions arbitrarily, like write a poem about dogs, and then produce responses to those instructions, like a poem about dogs, and then training that same model to now imitate its own behavior. And they use some tricks that like make this work. And I think one of the key tricks that I'll zoom in on here is that when you're doing data set generation, the most obvious thing to do is you first generate the inputs, then you like pseudo label your outputs. But the issue here is that the quality of your labels is only as good as your teacher is. So if I first generate a text and then I generate the class that I think corresponds to that text, if this class label is like really bad and maybe in like very systematic ways, as was mentioned earlier, then the training data will be really bad and you're not going to be able to learn anything useful. But when you're generating data, you don't need to actually do this linear process. You can instead first generate the class and then generate inputs conditioned on that class. So like this is kind of doing things backwards. And you can't do this when you're doing real prediction because you don't know the class. Like this is not useful in practice when you're doing prediction. But for generating data, you don't need to do things linearly. And so I think that this idea to me is like really important in data set generation. That you can decompose your task into different patterns or orders and then generate your data from like the ground up that way. And hopefully this way, by like reducing a hard problem to an easy problem, you can do a lot better. This is related to one other paper that I did not put in the slides. And so in this paper, they call this idea task asymmetry, where if you have a task of going from X to Y that is really hard, but going from Y to X is easy, then you can just start with a bunch of Ys, generate synthetic X's, but because this direction is easy, you can probably do pretty good at this. And then you can now flip the data again and train your model to generate Y from X. But you have a lot of data that is like pretty good. And then you can do like really surprisingly well using this strategy. So in like this paper, they were doing information extraction where you had you're given like sentences and you wanted to extract triples. So here, like you had what film, what's the location of that film, and so doing this sentence to information extraction is pretty hard, but it's pretty easy to be given a bunch of entities and generate a sentence about those entities. That's like pretty trivial to do, I think, with large language models. So they went backwards and they just took a bunch of triples, generated text synthetically, and then flipped the order of the labels and inputs. And then what they found is that in terms of the performance here, it's like double as good as the previous best model here, which was already really good for the time. So I think that this is like sort of an idea that I want to pass on that I think is really nice, that was touched on by Self-Instruct. Okay, and then the going a little further in this idea of using distillation to do things that you couldn't do before is some work that I did with Graham this past year, which is called prompt model. And the idea here is that let's forget that distillation is anything but just like a data set generator. And now distillation is one way to get training data for your model. But there might be other ways to get data as well that we're like leaving on the table. So I think the key idea here is, can we combine retrieved data, existing data that exists on the internet, with data generated from an LLM? And can we put these two things together and do even better? So in this paper, we ask the user to specify their task in a prompt, kind of like what you'd use for GPT-3. And they can give a couple examples if they want. And then given this prompt, we first retrieve existing data sets that might be relevant to that prompt. So we had like a method for data set retrieval in a previous paper that just uses text to find similar data sets. So if I say, answer biomedical questions about for cancer doctors, it might find like the BioASQ data set. And then we take that retrieved data set, which is likely to be high quality, but may not match the task that the user actually cares about. It might be like a little bit different than what the user actually wants. We then complement this retrieved data set with generated data generated by a language model, which is potentially like not that high quality, but is much more likely to match the user's intentions. We then did one other thing that's not that important, which is retrieving like a pre-trained model as well. Like maybe you have a pre-trained model that is in your domain that you can actually benefit from. Then we just put all these things together, fine-tune this small model on your generated and retrieved data sets. And then I think the really cool thing here was that we were able to obtain small models that often outperform GPT-3, even though GPT-3 was the model used to generate data. So like we were beating the teacher by leveraging like both distillation, but also taking advantage of existing data sets that were available on the internet. So I think that generally this is a direction I'm really excited about, distillation for the purpose of advancing model capabilities. And I think that this kind of came at a time when distillation was becoming really popular, but now it's often used by a different name, which is called synthetic data generation. It's effectively the same thing as hard target distillation, but this is like probably one of the hottest research topics in NLP right now. And just like last week, I saw this paper on the internet that provides like a sort of PyTorch-like toolkit for doing distillation. So they define different like primitive operations, like generating stuff from prompt or from RAG, doing retrieval, doing filtering and ranking of examples, or judging the input, like judging your generated examples using another LLM. And they also integrate model training into this loop. But I think that this is like a really exciting direction in terms of making data set generation something that can be very mature and like manage like a real engineering problem. Yeah, so I think that for like final projects, I think this synthetic data is a really exciting direction, and this kind of toolkit could be something to consider for if you decide to go that route. Okay, so we have a couple of minutes left if anyone has questions. Otherwise, that's it.